Welcome to our lesson on continuity, specifically what happens when graphs are not continuous. If we are tracing them and we have to pick up our pencil for any reason, then our graph has a discontinuity. There are three types of discontinuity. We can have a hole in a graph, we can have a vertical asymptote, or our graph could be a piecewise function, which looks like two separate graphs, two pieces of a graph, and they don't connect. The first kind we're going to look at is that infinite discontinuity, and you might recognize this from Algebra 2. We are tracing our graph, and we're coming in, and we avoid this value of x by going to negative infinity. In order to keep drawing the graph, we have to skip this value of x, pick it up on the other side at positive infinity, and come back down. Because we had to pick up our pencil, and because the ends go to positive and negative infinity, we have a vertical asymptote. And that vertical asymptote is called an infinite discontinuity. We might also see a hole in the graph. We're tracing our line, and we get here, and for some algebraic reason, we are not allowed the value of x equals 2, so we skip it and we pick up on the other side. Oftentimes, we'll see that there's a replacement value somewhere, maybe down here or above, it doesn't matter. But the idea is because we skip that spot in the graph, we have a hole, and that hole is known as a removable discontinuity, as though someone has just removed one value from our graph. The last kind of discontinuity we'll see is called a jump discontinuity. It occurs when we have piecewise functions, two different pieces of two different graphs that don't connect, different y values from the left and the right-hand side. If we were tracing a, this is a linear function with a negative slope, we're coming down, and we stop here at this value of x equals negative 2, and in order to continue the graph, we have to jump down, still at x equals negative 2, and pick up this quadratic graph to keep going. So our pencil jumped at x equals negative 2, and that's our jump discontinuity. Now, we need to be able to check for those jump discontinuities without having to go through the trouble of creating the piecewise graph. We're going to see how we do that in example B. This is a piecewise function. You'll see there are two functions, two pieces. They're both linear. The top line only exists where x is greater than 2. There's no equal sign there, so we would know that this graph ends in an open circle. And this graph down here, this linear function that has the equal sign, would end in a closed circle. That's not really important. What's important is what happens at this transition where x is 2. And we want to know, do these two pieces meet or are they separate? So we're going to see what the y value is for the top function and for the bottom function at that transition by plugging in 2. So for the top function, we plug in 2 for x. We've got 2 plus 4, which gives us a value of 6. So that graph exists at a point of 2, 6. If we go to our second function and plug in 2, where the x is 2 times 2 minus 3, this graph goes to 1. Now, 6 is not equal to 1, so if we were drawing that, we'd have to jump from a value of 6 to 1 to create this graph. So it has a jump discontinuity that happens at x equals 2. We've checked that out. That was the transition. Here's the same idea, but with a quadratic function and a linear function. We can see the quadratic function would end in an open circle, the linear function would end in a closed circle, and the transition is at negative 1. So remembering PEMDAS, we'll plug in negative 1, square that and subtract 2, gives us a value of negative 1 for the quadratic, the first function. For our second function, we'll plug in negative 1, and we'll get negative 1 as our answer. Now those two are equal, so these two graphs are going to meet in the middle. So there's no discontinuity, they meet. So we're going to label that graph as continuous. In addition to finding those algebraically, we just need to identify them and label our discontinuities when we look at a graph. In number 1, we're tracing our graph. We come down here and we have to skip over just this single value. It's been removed from the graph. That's our hole. So we're going to say there is a removable discontinuity. And we want to be specific about where it is. always an x value at x equals -2. Now this piece of the graph ends right here at an x value of 1, and our pencil has to jump up to keep tracing the graph. So for this piecewise function, there's also a jump discontinuity, and that's at a value of x equals 1. So we can have more than one. We can see in the second graph that our graph goes to negative and positive infinity on either side of these two vertical asymptotes. And because we're going to negative and positive infinity, we're going to label those as infinite discontinuities. There are two of them. At x equals -3 and at x equals +3. Sorry about my bad handwriting. All right, number 3, you might recognize this as an absolute value graph from Algebra 2, and you are correct. But each absolute value graph could also be thought as a piecewise function with a line of a positive and a negative slope. So here's our line with a positive slope, and right here we transition at x equals 1 to our line with a negative slope, but we don't have to pick up our pencil. They meet in the middle. So this graph has no discontinuity. So we're going to say that's continuous. All right, the last thing we're going to do is just a little bit of extra practice with algebraic definition of discontinuity. Can we find them just by plugging in values? So again, we're looking at our transition point in example number 4. The transition is at -1. And we want to see that this graph ends in an open circle, that ends in a closed circle. What happens at -1? -1 squared minus 4. That gives us a value of -3. Then in our linear function below, we are also going to plug in -1, -2 minus 1, -3. Those are equal. The two graphs would meet, and this is continuous. And in our last example, we've got a quadratic and an absolute value. We can make a piecewise function out of any functions that we know. So this one, open circle, closed circle, and the transition is at -3. So remembering PEMDAS, we're going to plug in -3 and evaluate for the quadratic function. 9, oh, I don't know how I got that line, -6 minus 10, 3 minus 10. So that graph stops at a y value of -7. Looking at our other graph, absolute value, remember those operate like parentheses. We're going to do the operations inside first. We get +8 plus 2, giving us 10. So if we were tracing this graph, we'd have to jump up from -7 to 10. Those are not equal. So we have a jump discontinuity at that transition point of x equals -3.